So the syllabus content for the third chapter, we going to look, we will divide it into 6 sections. The first section, we're going to look on the convection principle of the heat convection coefficients. And then we're going to look on the convection boundary layer theory, force convection over exterior surface laminar flow, cause convection in turbulent flow, principal dynamic similarity applied to force convection, and finally free convection over a flat plate. Bear in mind that the syllabus does not contain, because thermal engineering is the combination between the thermodynamics plus with the heat transfer. So the heat transfer, force convection for internal flow does not cover in this chapter. Then the student is required to do the self-learning to have the knowledge for the interior convection of heat transfer. So the convection, the first section, we're going to look on the convection principle, which is the heat transfer coefficients, which is developed by the Nusselt. Okay, so this is Wilhelm Nusselt. He was born in Germany in 1882 and died in 1957. So in convection analysis, is a common practice to non-dimensionalize. So this is not just with the heat transfer, but also for all engineering practice, yeah, to have non-dimensional parameters that collates all the what call that, the variables. Okay, so this is a combine of the variables that we group together in dimensionless and quasi-dimensioned numbers. So by doing this, we can do the mapping and we can reduce the number of variables so that it becomes parameters. So Nusselt number is one of the non-dimensional parameter, which is introduced by Wilhelm Nusselt. So the Nusselt number is the non-dimensionalized H, which is the ratio between the heat convection to the thermal conductivity. So it gives the character where L is the characteristic length, H is a convection coefficient, and K is the thermal conductivity of the fluid. So we have several conditions. Okay, so with this one, which is actually the ratio, it giving the replication of the ratio between the heat of the convection and heat of the conductions. So heat transfer by conduction occurs when the fluid is motionless and contact each other, and heat transfer by convection occurs when the fluid involved with some motions. In either case, the heat flux is the rate of the heat transfer per unit time in the per surface area. So taking into the ratio that between the heat convection and heat conduction, H times with the delta T, and then K times delta T over L, where we got the HL divided by K, and this is represented by the Nusselt number. So does Nusselt number represent the enhancement of the heat transfer through the fluid layer as a result of the convection relative to conduction across the same fluid layer? The larger the Nusselt number, the more effective will be the convection. So the Nusselt number equal to 1, which is giving the representation of the pure conduction, which is the rate of the heat convection is equal to the rate of the conduction. So let's move to the second section, convection boundary layer theory. As for the convection analysis, it is going to involve with the external flow and internal flow, which is actually, so then it is going to involve with the flow layers of the flow passing through several cases. In this fundamental aspect, we're going to look a flow passing through a flat plate, and as well a flow passing through various form of the object. So consider that we have a flat plate, okay, and then this flat plate is passing through with the free stream velocity u infinity. When it passes through the surface of the flat plate, a velocity boundary layer will be developed where near to the surface the velocity will be equal to 0 according to the with assumptions of the no slip conditions. Okay, so with that, the velocity at the surface or nearby to the surface u is equal to 0. So u in the y directions. Okay, so as the distance far away from the surface, the velocity will be developed. Okay, so u until it reach to u infinity, where it is equal to the free stream velocity. Okay, so this when the boundary layer thickness will be considered when the velocity is equal to 99% of the free stream velocity, or the local or the y directions velocity is equal to 99% or 0.99 of the free stream velocity. Okay, so if this velocity boundary layer will be developed from the starting point of the flat plate until to the infinity, growing through the direction of the free stream velocity. Okay, so it is also depends on the type of flow. So later on we're going to look on the conditions. Okay, so that's for the velocity boundary layer. As for the this one, okay, this is a velocity boundary layer where we have a dashed line divided the flow over the two regions of the flow, where we have the lower part section, which is the area that we have with the boundary layer, and the upper side where we have the section that where we have the inviscid flow regions, in which the friction effects are negligible and the velocity remains constant, where the velocity is equal to the free stream velocity. Okay, so let's say that the surface is heated. Okay, then what will happen that which according to the development of the velocity boundary layer, we're going to have three sections. Okay, so which is laminar section, transition sections, and turbulent sections, where through these laminar sections the flow is the velocity development is the velocity profile for the at this section is very disciplined, is very developed nicely. And then in the turbulent section, where we say that the velocity is increased rapidly, thus this is due to more energetic particles that they have in this region segment. So what will happen when there's more energetic particles? So one particles is try to taking each other. So in these sections, when one more particles has more energy than the other particles, it try to take another particles, then it will create a chaotic flow. So this chaotic flow we call as the turbulent regions. So in this turbulent region sections, the flow is chaotic and the velocity profile is not developed as the laminar flow regions. As for the between the laminar flow and turbulence flow, we have the transition flow. Okay, so in these transections where some of the particles has a little bit energy than the other particles. It try to taking each other, then it create in between some of that we have a good growth of the velocity profile, and some of the region will have the kinetic flow sections. Okay. So what we have here is that comparison between the laminar and turbulent flow for the boundary layer profile, where we have a steady growth for the laminar flow and unsteady growth, where in these sections, in order to do the calculation, to have the velocity prediction for y directions, the average velocity will be taken consider for the velocity boundary, for the turbulence sections. Okay, so let's look. That is for the velocity boundary layer. So if we have a heated surface, then with incoming free stream velocity u infinity, then this free stream velocity also exists with the free stream temperature or the surrounding temperature. So this surrounding temperature actually is far from the surface section, heated surface section. So what we have here is the and this T infinity is less than T surface section. Okay, so this is a Ts. So throughout this Ts, the surface heated surface temperature, the heat will be transferred from the heated surface to the surrounding. So thus the temperature varies from the near to this section until it reduces until to the free stream temperature. So this is what we call as the thermal boundary layer. So because the velocity and the fluid is zero at the point of the contact, so thus at the point of the contact for the fluid in the flat plate heated surface, the temperature for the fluid is assumed to be similar as the surface temperature at that contact point. So with that, what we can see here, we can have a similar thermal boundary layer development on a flat plate similar to the velocity boundary layer, but the profile will be a little bit different because the heated surface and the the velocity boundary layer, the no slip condition for the velocity boundary layer is started at the zero, but for the velocity boundary layer it is started at Ts, where you have a free stream temperature. It passing through this section, we have a free stream temperature T infinity and the surface temperature of Ts. Okay, then you have a temperature profile for the thermal boundary layer where it is in the reducing conditions. So the thermal boundary layer is measured, okay, when the difference between the T infinity minus Ts or T stream temperature to the T surface is about 99%. Okay, so as compared with the velocity boundary layer, it is when 99% of the velocity is equal to 99% of the free stream temperature, whereas for this one is a 99% is equal, or when the T infinity is approaching to the free stream temperature. All right, so let's look on another important parameters for the convections heat transfer, which is the Prandtl number. So the Prandtl number is developed by Ludwig Prandtl. He was born in 1875 and died in 1953. So what does it mean by the Prandtl number? Is it the ratio of the molecular diffusivity of momentum, okay, which is given by this one, kinematic viscosity, divided by the alpha, where alpha is the molecular diffusivity of the heat, where it is thermal conductivity divided by the Cp. Okay, Cp is the rate of the heat, constant rate, constant heat at the Cp is the heat at the constant pressure. Alright, so the relative thickness of the velocity and thermal boundary layer is best described by a dimensionless Prandtl number. Okay, so what does it mean here is that when the Prandtl number of gases is more than 1, which means that indicate that both momentum and the heat dissipate through the fluid at about the same rate. And then the heat diffuses very quickly in the liquid metal because of the Prandtl number is less than 1. And then when the Prandtl number is larger than 1, the heat slowly diffuse because of the value for the constant heat at the constant pressure is lesser than the momentum. Okay. So consequently, the thermal boundary layer is much thicker for the liquid metal and much thinner for the oil relative to the boundary layer conditions. So another important parameters is the convection principles. In the convection principles is the Reynolds number. Sorry. So the Reynolds number is derived by the Osborne Reynolds. He was born in 1842. And died in 1912, so he's a British. It replicates the transition from laminar to turbulent flow that depends on the surface geometry, surface roughness, free stream velocity, surface temperature, and the type of the fluid. So however, the flow regime primarily depends upon the ratio of inertial forces to viscous forces in a fluid. So this is a dimensionless quantity known as described by the Reynolds number. So the Reynolds number giving you the ratio between the inertial forces to the viscous forces, where VL divided by V, or rho VL divided by mu. Okay, so rho VL is the initial forces and mu is the viscous forces acting by the fluid on the surface. V is the velocity, rho is the density of the fluid, L is the characteristic length, and then mu is the dynamic viscosity, and then V is the kinematic viscosity. So the dynamic viscosity, or mu, okay, is the shear force per unit area that required to drag on the layer of fluid with the unit velocity passed to another layer. So which means that if the slope for du over dy is larger, then the kinematic viscosity will be smaller. Okay, so in that case, when you have a small growth of the velocity profile, so the kinematic viscosity will be, the dynamic viscosity will be lower, or you have a bigger stress. Okay, kinematic viscosity, the kinematic viscosity is the ratio of the dynamic viscosity to the density. Okay, so which means that a larger density with a similar value of the dynamic viscosity will be reduce the kinematic viscosity, or vice versa. So a larger number of the Reynolds number, which means that the initial force is large, which means the viscous force cannot contain random and rapid fluctuations, then this will give the turbulence conditions. So in other words, the energy of the particles become larger, and then it will create the turbulence or chaotic flows in the that sections. However, with a small condition where we have bigger viscous forces or smaller initial force, we will have a smaller Reynolds number, which means that the flow growth will be in discipline manner. In that case, it will create a laminar flow regions. Okay, so the Reynolds number where the flow becomes turbulent is called as the critical Reynolds number. So there is difference between the critical Reynolds number between the external flow and internal flow. So as for the external flow, the critical Reynolds number is 400,000, and then internal flow is about 3,200. Okay. Oh, sorry. My mistake. Is a critical Reynolds number for the external flow is 5 times 10 to the power of 5. Okay. So the Reynolds number where it is depend on the density, velocity, x, and dynamic viscosity, where x critical is the distance where the leading edge of the flat plate of the plate to the transition point from the laminar to the turbulent flow takes place. Okay, so let's finish that for the principles. Let's move to the condition where we have the flow over exterior surface in laminar flow region. So the convection equation for external flow can be derived from the conservation of mass, conservation of energy, and conservation of momentum equations. So the convection over a flat plate where we have U infinity and T infinity, that we create a boundary layer, thermal boundary layer, and a velocity boundary layer. Okay. So to consider laminar flow over a flat plate when viscous dissipation is negligible. So at the initial conditions on the surface where the U or velocity in the y direction is equal to 0 and the velocity in the x direction is at x point is equal to 0. However, the flat plate is heated. So thus we have the Ts temperature on the flat plate. Okay, and the flow is running with the steady incompressible laminar flow with the constant properties of a flat plate. So thus the conversion of a flat plate from the continuity equations, okay, momentum equations, and the energy equations. For this, applying with the boundary condition at x equal to 0, y equal to 0, and at y equal to infinity, where we have the velocity profile and as well with the temperature conditions at boundary conditions. Okay, with the defining of the dimensionless similarity, which is a neta equal to y square root of U infinity divided by the kinematic viscosity times with the x. So what we have, if we have a stream function, recall that the stream function is defined as the U, and for the y direction and v for the string function in the x directions, where we have different dependent variables. Okay, so I will skip this one and not going to explain on this one. Sections where we will have the boundary layer thickness for the flat plate, which is applicable for the laminar flow equations, where the boundary layer thickness delta is equal to 5 divided by square root of mu infinity kinematic viscosity times with the x, which is equal to 5.0 times with the x direction and divided by the Reynolds number, where the Reynolds number is given by these equations. Okay. So if we apply the energy equations, where it is a temperature difference between any point from x and y direction to the surface temperature divided by the free stream temperature and the surface temperature. So with that, applying into the energy equation and once again applying with the similarity variables, so we can use with the energy equations, that actually the derivation you can look on the from the PowerPoint slide, where the Prandtl number, which is the kinematic viscosity divided by the dynamic diffusivity, that we have a closed solution which is d theta over dn, which is equal to 0.332, Prandtl number 1/3, but this is still not solved yet. With that, what we have are solutions for the local convection coefficient and the Nusselt number, where we have H convections, which is 0.332 times with the Prandtl number to the power of 1/3 k u infinity divided v times with the x. So if we take the convection coefficient ratio by the thermal conductivity, the Nusselt number for the Prandtl number more than 0.6, which is given by we give the Nusselt number equations, where it will equal to 0.332 times with the Prandtl number power of 1/3 and times with the Reynolds number to power of 1/2. So the local friction number CPF, local friction coefficient, sorry, for the laminar flow can also be determined with the wall shear stress, where wall shear stress is given by T wall is the dynamic viscosity times with the gradient of U over dy, which is the shear stress, the wall shear stress is given by these equations. So similarly, the function f and its derivative for the laminar boundary layer for the flat plate can be similarity for the function f and the derivative laminar boundary layer along flat plate is given by this table. Thus, the local skin friction coefficient can be determined by these equations, okay, which is given by 0.664 times with the Reynolds number to power of negative 1/2. So if we take for overall of the flat plate, which is from 0 to L, okay, which the previously is a local convection coefficients. So if we want to calculate with the overall convection coefficient for whole length of the flat plate, you can do the integration from the previous equations, which is give you H 0.332, Prandtl number to the power of 1/3 times with K and divided by L, and you subtract with the Reynolds number. Okay, then it will give you the average Nusselt number for the laminar flow over the entire plate, which is Nu equal to HL over K, which is equal to 0.664 times with the Reynolds number to the power of 0.5 and Prandtl number 1/3. Bear in mind, this equation only valid when the whole flat plate in the laminar flow conditions, which is mean that the length or the length of the flat plate is less than X critical. So by using the velocity boundary layer, we can calculate the thermal boundary layer, okay, for the laminar flow region conditions, where the thermal boundary layer is given by these equations. Okay, so this is a guided example. Calculate the heat transfer where we have a flow at 4 meters per second and a free stream temperature of 40 degrees Celsius. The flow passes through a flat plate where the surface is 80 degrees Celsius in the X direction, passes through the X direction, and the length of the flat plate is 50 meters. Okay, so calculate the heat transfer and the thermal boundary layer thickness 1/4, or a quarter of the long way away, a quarter of the way along a flat plate that is 50 meters long. Okay, so in the cross-section view, you have a schematic diagram, 50 meters, surface temperature 80 degrees Celsius and 40 degrees Celsius for the free stream temperature. So initially you have to find a T-film condition, but in actual calculations, yeah, my suggestion, if you have in actual conditions, okay, when you do the design in your near future, when the only available temperature is the flat plate temperature, for example 80 degrees Celsius, so you have to do the iteration calculations. Okay, so thus your thin film temperature only will be considered for 80 degrees Celsius, but for this condition where you have this 40 degrees Celsius, then you can take the average temperature that we call as the T film temperature. So 80 plus 40 divided by 2, so it gives you the 60 degrees Celsius. Okay, so does it replicate? This is the first guess actually, but in actual engineering condition, you have to do several iteration calculations to get a refined result for your engineering solutions. So in the first iteration, when the thin film temperature is 60 degrees Celsius, then you can find in the liquid water at 60 degrees Celsius from the table the density, the dynamic viscosity, the thermal conductivity, and as well the Prandtl number. Then you do the calculation for the Reynolds number and check whether at 1/4 is it in the laminar flow region or is it in the already in the turbulent flow regions. Okay, so since the Reynolds number is about 10,500 and it is less than 5 times 10 to the power of 5, so it is still in the laminar flow region. Okay, so the convection of a flat plate, the Reynolds number, if you consider for the whole plate, we give you about 42,111. So the whole section over the entire flat plate is the laminar flow region. Okay, so you can apply the equation that we used before that we have derived before, sorry. So that for 1/4 you can do the calculation, and as well you can calculate for the entire flat plate. Okay, so then you have the H value, then you can calculate the heat flux for the flat plate or the rate of heat transfer in the convection conditions, which is giving you 34.8 watt over meter square. Okay, so I give you there are going to be several assignments for this online learning. So this is going to be your first assignment. Okay, so please download it and then look at this assignment. It is not available in your PowerPoint. It only can be accessed in here, so you only can see the assignment in here. So take your time, have a snapshot, and then do this assignment. Okay, so there are, for this assignment convection 1, there are 2 questions. Okay, the first question involved with the flat plate with the engine oil. Okay, and this is the second one with atmospheric pressure with the air. Okay, all right, so let's look. Previously we have looked on the laminar flow conditions. Now let's move to the flow over at the turbulent flow conditions. Okay, so we're going to analyze with the 2 conditions. The first one with the flow that is completely in the turbulent flow region, and we're going to have a mixed laminar and turbulent flow, where in this mixed laminar and turbulent flow, where in the first section you have a laminar flow growth, and then in the second section you have a turbulent flow section. So what does it mean by the turbulent flow? So before the turbulence or in the laminar flow condition, you have disciplined particles. Okay, so the flow in each particle, they are very well disciplined and follow the streamline. But when they have more energetic, okay, you can see that the flow is trying to take over, or the particles try to take over each other. Okay, so it creates a chaotic conditions. So this chaotic condition is known as the turbulent flow. So I go straight to the equation. For the flow that is all over the plate with the turbulence flow condition, when the Prandtl number is in this region between the 0.6 and less than 60, the Prandtl number, and the Reynolds number between 5 to 10, 5 times 10 to the power of 5 and less than 10 to the power of 7. So the turbulent flow equation, sorry, the Nusselt number equation for this condition is given by this equation. Alright. However, when the mixed flow condition, where a part of the flow is in laminar and another section is in the turbulence, so this equation can be used. Okay. So this is another guided example where you have a flat plate running with the oil flow over 40 meter long heated flat plate, streams condition at 5 meter per second and 25 degrees Celsius. If the flat plate surface temperature is 45 degrees Celsius, the free stream velocity is 5 meter per second and free stream temperature is 25 degrees Celsius. The length of the flat plate is 40 meter. First, determine the velocity and thermal boundary layer thicknesses at the middle of the plate. Okay, middle of the plate, which means that 20 meters. calculate the distance where the laminar change to turbulent flow. So you have to determine X critical. And C, calculate the total convection heat transfer for a 1 meter long width. Okay, so if the flat plate width is 1 meter, calculate the Q. So initially you need to find the film temperature, which is the average temperature between the free stream temperature and the surface temperature. And then after that you have to get the properties. So at the middle of the plate, which is 20 meters, you do the calculation for the Reynolds number, which is given by here, which is this is in the laminar flow region. Okay, because this is less than 5/10 to the power of 5. So you can calculate the what is it? This is a velocity boundary layer and as well the thermal boundary layer. Okay. At the end of the flat plate, the Reynolds number is 5.714 times 10 to the power of 5. So this is higher than the critical Reynolds number. So it is already at the end of the section, is already in turbulent flow region. Then you can calculate the critical length, which is giving you 35 meters. So 35 meters from 35 until 40 meters, that region is in the turbulence region. So thus you can calculate the mixed Nusselt number equation for the flat plate, okay, which is give you this value. Then using the Nusselt number equation, you can calculate the heat convection coefficient for the flat plate, which is give you 68.7. Then you can do calculation for the rate of heat transfer for the convection, which is 54.9 or about 55 kilowatt. Okay. Alright, so that is for the flat plate. There is another condition where you have the engineering problem where the external flow will pass through the external form of the body. So we're going to analyze here the forces, the flow that passing through cylinders, spheres, and as well some other type of form cross sections like hexagon, something like that, and as well rectangular. So flow across the cylinders and spheres in general involve with the flow separation, which is difficult to handle analytically. So if you're going to derive it, so it's going to be a long derivation. Okay, so what they have done, okay, so the researcher has done the empirical correlations. So this empirical correlation has been conducted by the correlating between the measured variables, and then call it to become as the parameters. Okay, what kind of parameters? So we're going to see later on. They have conducted several experimentations, and this experiment has produced correlations. Okay, so this correlation to correlate between the heat transfer coefficient H value with the parameters. Okay, so what kind of parameters? It is the Reynolds number and the Prandtl number. Okay, so can you recall back the Reynolds number equation, which is rho VL divided by mu, and the Prandtl number is the which is actually you can derive it from, or you can obtain it from the properties. So the Churchill and Bernstein there are several researchers that have developed the experimental work to define the correlations between the Nusselt number and Reynolds number and the Prandtl number. Okay, so the first one is the Churchill and the Bernstein, which is the study on flow over a cylinder. Okay, if you refer to your textbook, it's equation 735. So this is referring to that equation. So it giving you these equations. Okay, whereby Whittaker has developed empirical correlation for the flow over a sphere. Okay, so this one flow over a cylinder and this is a flow over a sphere. Okay, it's slightly different with this flow over cylinder for the correlation, where they have to consider the velocity of the free stream velocity and the velocity near to the surface. Okay, so by that there are several types of the experimentation that have been done by Zhukovskas and Jacobs to define the correlation of the Nusselt number with the Reynolds number and Prandtl number. Zhukovskas and Jacobs have done their experimentation later after the Churchill and Bernstein, and they have improved a lot where they have done the segmentation in order to improve with the previous correlation, empirical correlation between the Nusselt number and Reynolds number and Prandtl number. So what they have done, they have put the range of the Reynolds number. Okay, so this is a range of the Reynolds number in order to improve the correlations. Okay, so this is made available in your textbook. So first one, they have the cross section, a circle cross section, or in other words, with a cylinder with the circle cross section, and cylinder with the square or conduit. And they also try with the square with the tilted 45 degree. Okay, and then hexagon tilted, vertical plate, and ellipse. So you can see, you can look here the correlation of the Nusselt number and the Reynolds number. So you don't have to remember it, memorize it. So if you come for the final exam, this is made it available. And as well, if you're referring to in the future when you become as the engineer, you're going to look this equation easily from you can find it easily in the standard. And this is the guided example for the force convection. Let's say that you have a 10 centimeter diameter hexagonal steam pipe whose external surface temperature is 110 degrees Celsius. The free stream temperature is 10 degrees Celsius and 8 meters per second for the velocity. So the length is 10 centimeter diameter. Okay. In general, you need to find the thin film temperature, which is give you 60 degrees Celsius, and then after that you need to find the properties from the table. Then you do a calculation for the Reynolds number. Then you can refer to the textbook, refer to the table in order to get the correlation for the hexagon and with respective Reynolds number range, which give you the correlation of the Reynolds number for the hexagon cross section, which is this one. Okay, then the correlation for the heat convection coefficient with the Nusselt number. You calculate the cross-sectional area. Then finally, you can calculate the rate of heat transfer for the convection. Okay. Alright, so there are several assignments that I will give you based from the section being described here. So you're going to have the second assignment also submit by 30 of April 2020 via Google Classroom. You can upload that. Please register to. I believe that most of the my student already register with the my Google Classroom, but for other student, please contact with your lecturer. Okay, now let's move to the section 5, which is the principle of the dynamic similarity applied to the force convections. Okay, what is the intensity of this section? Which is actually um, what you have seen before. The derivation of the heat convection coefficient for the flat plate is easily derived, and then move to the next section when you have the external flow where the empirical correlation have been developed by previous researcher. Okay, so in this section will tell you how that the previous researcher have developed the um, empirical analysis in order to give you the empirical correlations for the Nusselt number, Reynolds number, and Prandtl number, or in other words, the empirical correlation of the parameters. Okay, so this empirical correlation has been developed by using the non-dimensional conditions. Okay, from the continuity, momentum, and energy equation for steady, incompressible laminar flow of fluid. So it can be non-dimensionalized, which is by dividing or that dependent and independent variables. Okay, for example, the length. Okay, you can non-dimensionalize the length, the velocity, and as well with the pressure and the temperature. Okay, so you can modify the continuity equation, the momentum equation, and as well the energy equations. Okay, so thus we replicate for non-dimensionalized conditions for the velocity boundary layer conditions. So similarly, you can do the modification for the Reynolds number. Okay, so Reynolds number similarity is very common, and as well the Prandtl number, which is this is a non-dimensional condition, kinematic viscosity divided by the thermal diffusivity. For a given geometry, the solution for a problem with the same Reynolds number and Nusselt number are similar. Thus, Reynolds number and Nusselt number are called the similarity parameters. For with this condition, we summarize, it will simplify for you, for the engineers, for the users to use with to accommodate with their conditions. Okay, when you do the mapping in your engineering problem. Okay, so the two physical phenomena are similar if they have the same dimensionless form of the given differential equation and the boundary conditions. Okay, so a major advantage in non-dimensionalizing is that the significant reduction in the number of similarity parameters. Okay, so when you do the mapping, you put the presentations, it becomes less presentation. It can be simplified your presentation wise. Okay, and then it can make a similar condition, for example, for the actual conditions with the experimental condition. Of course, for example, if you are simulating or if you're bringing the experimental or the actual problem, engineering problem that involve with the larger scale of the uh, larger spec or larger physical parameters, then you can simplify it in small physical parameters in the experimental work. Okay, for example, if you want to scale from the actual condition that use air, and then you want to scale down by using the water, and then have a smaller physical dimensions, and the Reynolds number is maintained. Okay, all right, so some examples of determining the convection heat transfer coefficient. So for flow over a given surface, we require a numerical solution for the velocities, for the surface length, for the wall temperature, and as well for the field streams temperature. So with this, we can collect, and it becomes only with the Prandtl number and the Reynolds number. Okay, so let's move to the next slide. So similarly, when we collect combine all the parameters for the length, velocity, temperature, kinematic viscosity, dynamic viscosity, thermal diffusivity, and it can become as the Reynolds number and Prandtl number. So only two parameters can represent all that lot of the variables. Okay. So thus we can, like for this example, this plot showing the presentation of the characteristic of the drag coefficients with the Reynolds number. So in this slide depicts an example, two examples of the wind tunnel experiment to measure the drag force acting on the vehicle model, and drag forces measurement to calculate or to measure the wall drag force. Okay, so which is CD drag for the pressure is equal to 0, and then CD friction, which is equal to CF, where the CF or the that can derive for the friction force, which is given by the CF times with the surface area rho v squared over 2. So in force convection analysis, we are primarily interested in determination of the quantities of the coefficient frictions in order to calculate the shear force. Okay, so in the previous slide, we have seen the correlations between the shear force and the Nusselt number. Okay, so Nusselt number to calculate the heat of the rate of heat transfer. Therefore, it is desirable to have a relation between the friction coefficients and the Nusselt number. So then we can calculate one when the other is available. So by doing the experimentation work using the Reynolds number analogy, we can define the Reynolds number or the Nusselt number by determining the friction coefficients. So the friction coefficient can be determined when you can measure the friction force. Okay, so this is given by the shear stress surface, where the friction coefficient is the function of length and the Reynolds number. Okay, so skip this one. So the friction coefficients is the function of the Reynolds number and the Prandtl number, where throughout the experimentation work, this is a common sum of the correlations that have been used with the with the function of y equal to a, and then you have the correlation of x to power of m and b to the power of z and to the power of n. Okay, something like that. Okay, so this one is better. Make it better one. A, B, Z to the power of n. So this has been commonly used when researchers want to get the correlation for their experimental work by correlating with the non-dimensional parameters. Okay. So in this case, the local Nusselt number is assumed to have with the correlation with the length, Reynolds number, and the Prandtl number, and for the local Nusselt number, and average Nusselt number with the Reynolds number and the Prandtl number. So thus, a common Nusselt number is the ratio between is the correlation between C Reynolds number to the power of n and the Prandtl number to the power of n. So this is what you have seen before when the researcher developed the correlations of the Nusselt number between the Reynolds number and the Prandtl number. Okay. So with the force convection, the Prandtl number, if the Prandtl number is equal to 1, by using the similarities analogy, dimensionless analogy, that we can have the Nusselt number correlation with the friction times with the Reynolds number divided by 2, which is give you the Prandtl number, okay, which is friction divided by 2. So this is a Prandtl number is modified, has been developed by the Edward Stanton, born Sir Thomas Edward Stanton, born in 1865 and died in 1931, where they have Sir Thomas Edward Stanton has modified the Reynolds number combined with the Nusselt number. So the Stanton number gives you the H convection coefficient divided by rho Cp times with the V infinity, or it is correlation between the Nusselt number divided by Reynolds number and the Prandtl number. So when the Prandtl number is equal to 1, it's important that because it allows us to determine the heat transfer coefficient when the Prandtl number equal to 1 from the previous knowledge. Okay, Prandtl number. Okay, so that recall that the equation for the friction coefficient before, where Cfx is equal to 0.664 times Reynolds number -1/2 power, that we have also the Nusselt number 0.332, Prandtl number 1/3, and Reynolds number 1/2. Okay, and taking this consideration, we can combine this equation, and then this is proposed by Chilton-Colburn analogy, okay, or Colburn J factor, okay, where from this coefficient, friction coefficient divided by 2 equal to Nusselt number, Prandtl number, the power of -1/3, Reynolds number -1. So JH is Cfx/2, and then this given by these equations. So from this Chilton-Colburn analogy is only applicable for the laminar flow condition, where over a flat plate dP over dx is equal to 0, only condition, which means that there is no changes for the pressure. However, the experimental studies have shown that it is also approximately applicable for the turbulent flow, but it is not that much confident to use that for the turbulent flow region. For the laminar flow, it is not applicable unless it is only for the flat plate, because the correlation, which is based from the Nusselt number derivation. So also the analogy above can be used for the local and average quantities. So thus, if we do the experimentation work to define on the flat plate, that we can calculate the drag force, then we can correlate it with the Nusselt number. Only applicable for the flat plate. Okay, so this is an example that you can look, where the calculation for the drag force is given by this one, frictions, where friction coefficients given by this one, then applying from the previous equation, we can get the. Okay, so final section, we going to look for the free convection or natural convection over a flat plate. Okay, so free convection, let's consider hot air rises due to the buoyancy effect. Okay, so let's take a can from a fridge and then put it outside. and then the ambient temperature. There will be a heat transfer process happen, and then what you can see that a cold can and then a cool air when the flow approaching to when the air approaching to the can, the can temperature, the wall for the can temperature will have some kind of the heat transfer process by the temperature difference. Then it also create a buoyancy effect due to the free motion buoyancy effect that caused by the temperature difference. Okay, so that caused by the temperature difference due to the nature of forced convections. Okay, so for the for the free convection, volume expansion coefficient is defined by the 1 over V times gradient V over gradient T, which is 1 over rho minus 1 over rho gradient rho over gradient T. So it required a property to represent variation of the density of a fluid with a temperature at a constant pressure, and this is a volume expansion coefficient beta, which is defined as this equation. So if we take that, assume the natural convection studies, the condition of fluid sufficiently far from the hot or cold surface is indicated by subscript. Okay, so this is for the free stream conditions. Okay, then if we replace with the differential equation such as this one, where beta equal to 1 over rho difference of gradient rho over gradient T, then if we take the ideal gas equation of state, where PV is equal to rho RT. Okay, so the changes of this density, so ideal gas equation of state, then the discharge coefficient or volume expansion coefficient will become only, can be simplified as 1 over T. So in other words, the volume expansion coefficient for ideal gas equation of state is inversely proportional to the temperature. So the temperature profile from the hot plate, which has a high temperature, and the free stream temperature is the expansions will inversely of this temperature. So which the volume expansion will inversely from this temperature profile. So as in forced convection, the boundary layer thickness increases in the flow direction, but yeah, in here there is some velocity profile developed, whereas at the free stream velocity, the velocity is equal to 0, and near to the surface the velocity is equal to 0. The velocity profile developed in this region is due to the buoyancy effect. Okay, so the record with the momentum equations, which is given by this equation. Then momentum equation outside of the boundary layer, as a special case, when u is equal to 0, can be simplified by this one. And then it can be combined, the equation from momentum equation and this equation, combining with the expansion, where we have a non-dimensionalized x momentum equation, u velocity profile, and this one, where it gives you this new non-dimensional parameters known as the Grashof number. Okay, so this Grashof number is derived by Franz Grashoff, born in 1826 and died in 1893, is from Germany, where the Grashoff number is given by these correlations. Okay, so Grashoff number is a measure of the relative magnitude of the buoyancy force and the opposing viscous force acting on the fluid. Okay, and then Lord Rayleigh, born in 1842 and died in 1919, from England, has derived the Rayleigh number by modifying the Grashoff number and the Prandtl number. So it has become the Rayleigh number. Okay. So this is one of an example for the free convections that focus on the 6 meter length of the hot pipe section in a large room. The pipe surface temperature is 70 degrees Celsius and the free stream temperature is 20 degrees Celsius. Okay, the diameter of the pipe length is 8 centimeter. The thin film temperature is the average between the free stream and the surface temperature, which is give you 45 degrees Celsius. And you can look in the table to get the properties of the air. The volumetric expansion coefficient or beta is proportional to the thin film temperature. Characteristic length is the outer diameter of the pipe, which is 0.08. So thus the Rayleigh number is the Grashoff number times with the Prandtl number. So the correlation of the Rayleigh number and the Nusselt number is provided in the textbook. You can refer to this one for the horizontal cylinder. Okay, so this is the correlations with the conditions of the Rayleigh number less than 10 to the power of 12. So applying the equations, then you get the Nusselt number equal to 17.4. Then with that, the convection coefficient can be calculated, which is give you 5.869. You can calculate the surface area. Then finally, the rate of heat transfer can be calculated for the problem. Okay, so that's for the free convection or natural convection. So this is the last assignment that for this one. Also, we're going to use with the hot cylinder, diameter 15 centimeter and the length is 1 meter. So this is the third assignment. You have to submit via Google Classroom by 30th of April. Yeah. So I guess that will be all for the chapter 3 for the heat convection coefficients for the heat transfer by using the heat convection. So I hope that you're going to complete all the assignments. Then we're going to give you a project as well, so wait for the project. And then I hope that you're going to repeat this video several times. If you have any inquiries, please let me know. You can contact me through the WhatsApp or through the email, or you can ask the problem, or you can arise any question in the forum for the Google Classroom or in the island. Okay, so this is an example of the turbocharge. You can see that when it's running with the full operating conditions at, I think this is about 6,000 to 7,000 RPM. Okay, so you can see that the heat which is dissipated from this exhaust conditions. Yeah. So thank you very much.